All right, so last time we looked into the idea of electric field as just this ratio of force per unit of charge. Specifically, the electric force that would be felt by some test object divided by the charge of that test object. Or to put it another way, electric force equals the charge of the test object times this vector quantity called the electric field. And let's say we have an electric field already established. Let's say, well, first of all, let me just taking a look at what those would look like. If you've just got some positive source charge, what would the electric field caused by that look like? What would be the general shape there? If we think of the electric field as related to the force that would be felt by a charge at that location, for example, let's say we put a tiny positive test charge here. Which direction would that get pushed or pulled?
Pulled away?
Yeah, it's going to get shoved away from that source charge. And the electric force and the electric field are in the same direction if the test charge is positive. On the other hand, if we had a negative test charge, if this test charge we imagine putting there was negative, the force it experiences would be opposite to the electric field, since a negative multiplier just reverses the direction. So I would generally recommend imagining what happens if you put a small positive charge there. The direction that small positive charge would get shoved is the direction of the electric field at that point. And in this case, that's going to be outwards, away, wherever you put it. If you put a small positive test charge here, it gets repelled from the source charge. No matter where you put that test charge, and of course the electric field could be stronger or weaker. Like if you put the object here, it's going to experience a much stronger force. Put it further away, it's going to experience a weaker force, but always away. So what would that look like if we drew in a field line diagram instead of these vector arrows? All the field lines would be pointing in what direction? Well, what's the general trend of all these vectors? These electric fields, when drawn as vectors, they're all pointing in what sort of trend? What sort of direction?
They're all pointing outwards?
Yeah, all these electric field vectors are pointing outwards because a positive test charge would experience a force in the outwards direction. So the electric field is in that direction also. So these individual vectors could be thought of as electric field vectors. But it's often more convenient to draw the electric field as field lines. Instead of drawing in the individual arrows at every location, we just draw long curves or long lines with arrowheads showing the general trend. So this would be one way of depicting that electric field, just outwards in all directions. Or for more detail, we could fill in all the in-betweens, which would just also be outwards. You want to make sure you fill in the in-betweens evenly though. You don't want to like fill in this in-between but not the others. Because we should expect this to look symmetric. We should expect the drawing of the electric field to be symmetric in all directions because there's no difference in where the charges are in all directions. Generally, the electric field is going to have the same sort of symmetry as the arrangement of source charges itself. So this is generally what you would expect the electric field to look like when drawn as a field line diagram for a single point positive source charge. If the source charge was negative instead, so looking at a completely different situation, just ignore what we've already got, new diagram. If we had a negative source charge, what would you expect to be different?
Would it be the opposite of the positive cue? So point inwards?
Yeah, we're going to have the same general shape, but all pointing inwards instead of outwards. So looking something like this. Because again, if you imagine putting a small positive test charge nearby, that's going to experience a force. In this case, it would be an attractive force. And once again, if the test charge is positive, not the source charge, but the test charge, the one we're experimenting with, if the test charge is positive, then the force it experiences and the electric fields at that location are in the same direction, since a positive multiplier doesn't change the direction of a vector. Any questions on that so far? On the other hand, what if we were to put a negative charge here? Like let's say we make a negative test charge, put it right here. Which direction would that get shoved?
Would it go out or go backwards?
Yeah, that's gonna, because if you got negative and negative, same charge is gonna repel. So at this location, the electric field in this region is upwards, but this negative test charge experiences a downwards force, because a negative multiplier means these vectors will be in opposite directions. The negative test charge experiences a force opposite to the electric field. Positive test charge experiences a force in the direction of the electric field. Any questions on that so far? And also if you have multiple charges, like let's say you've got, instead of just one single point source charge, let's say you've got several source charges. For example, let's say you have a positive charge, and then over here you have an equal amount of negative charge. And we're not going to be looking at the attraction these have on each other. We're assuming these are both basically rooted in place. Maybe they're even like both attached to a stick. One common arrangement is to have a, let's say, a plastic rod that has positive charge on one end and negative charge on the other end. So this would be called an electric dipole. Or we would say that this object is electrically polarized. It has a positive pole and a negative pole. In that case, it's going to be creating a very unique electric field. If we treat this dipole as a source of the electric field, we would say each of these charged objects is creating an electric field, and together they're going to create their own overall electric field. So treating this dipole as the source of the electric field, first of all, if we were looking at just the positive charge, its electric field would be just outwards in all directions. And then getting weaker as you get further out. And then even weaker beyond that. And of course, this isn't to scale, but very approximately. And here I'm actually drawing in the individual vectors rather than just field lines, because we're going to want to see how these interact. Meanwhile, what would the electric field for the negative charge look like? If we ignore the positive and look at just the negative charge, what would the electric field near that look like?
It's going inwards?
Yeah, we would expect an inwards electric field. So nearby, it's going to be strong inwards in all directions. And then as we get further out, it's going to be weaker. And then if we get even further out, that'll be weaker still. And weaker the further out you get. But if we want to combine these, how would we figure out the actual electric field at each location in space? For example, in the middle here, the positive charge creates electric field to the right. The negative charge also creates electric field to the right. How would we combine those to figure out the actual electric field at that location?
Is it like 7b when we combine vectors together and they have like, yeah.
The actual net electric field at any location is just the electric field caused by A at that location plus the electric field caused by source charge B at that location. And this continues no matter how many charges you've got. If you've got an electric field being produced by 17 different source charges, at any given location, you just find the electric field, what we usually call the electric field contribution caused by each one of those source charges at that location, and then add all those together as vectors. So electric fields are additive in this way. And we generally call this the idea of superposition. Very similar to the idea of waves interfering with each other. If you've got multiple waves in one location, you can just add together their effects. Same idea here. If you've got several different electric fields contributing at one single point, because you've got several different sources, then you can just add together all of their contributions. So in the exact middle here, we've got electric field to the right plus more electric field to the right. If you add a vector to the right plus another vector to the right, what happens?
The vectors grow larger. It's like a bigger.
So in this region, in this in-between region, we're going to end up with a very strong electric field to the right, which ultimately in the field line diagram should be shown by having more densely packed lines here. The field lines are going to be close together. What about over here? If we've got a strong field line, a strong field vector to the left plus a weak one to the right, what's going to happen there? If you add a lot to the left plus a little bit to the right, what would you expect to happen?
The left arrows would kind of grow a bit shorter, but it would dominate over the arrows going to the right. Maybe?
Yeah, overall and we're not really talking about two different arrows to the right here. We're looking at just one location. So like at this location, we've got a large electric field to the left because of the negative charge, plus a small electric field to the right due to the positive charge, which is further away. So as you said, the one pointing to the left is going to dominate since it's larger than the other. They will partially cancel out because they're in opposite directions, but overall the electric field in this region will be to the left because we're adding a large leftward vector plus a small rightwards vector. But they're going to partially cancel out. So we should expect a somewhat weak electric field over here versus a strong electric field in between. And what about over here? If we're adding large electric field to the left plus a small electric field to the right?
It would just point to the left, but it would be more weak.
Yeah, same thing. We get a weak leftwards electric field, or at least weaker, not as strong as in the center. But note that we've got the same on both sides. On the left side and on the right side, as long as it's outside the region, is pointing to the left and it's somewhat weak. We could also take a look at other regions. For instance, let's say up here, directly above the center, we've got a vector pointing up and to the right, plus a vector pointing down and to the right. What happens if you add those together?
Could they cancel out maybe, or no?
They partly cancel out. It might help to think of these in terms of components. You've got up and to the right, plus down and to the right. When you add the y components, upwards plus downwards, what happens?
So they wouldn't cancel out, like the up, if you add the up and down together? They
would actually. If we're talking about just the y components, upwards, down,
okay.
And by symmetry, if we're talking about same distance from both of these, we should expect these to be the same strength.
Okay.
The positive y component and negative y component do cancel out. If you look at the x components though, you've got to the right and to the right. So when we add those, they don't cancel out, they combine. So what would the total vector look like there?
Would it just be a right arrow then?
Yeah, purely to the right. The vertical components cancel out, the horizontal components combine. So in this region, we get a vector straight to the right. In fact, that's going to be true anywhere directly above the center or directly below the center. Like down here, we also have down and to the right, up and to the right. The up and down components cancel out. The right and right components combine. Of course, the further out you get, the weaker that becomes. But near the center, it's going to be very strong. So we get a strong rightwards arrow near the center, and then weaker and weaker as we get further up or further down. And in terms of the field line diagram, we're going to show that by having the field lines spaced further apart when it's weaker, or spaced closer together when it's stronger. We could also take a look at anything, let's say, directly above or below one of the charges. For instance, let's say we look up here. We've got a downwards arrow from the left charge and an up and to the right arrow from the right charge. If we add those as vectors, down into the downwards plus a little bit up and to the right, our total, just adding those together head to tail, our total is going to be mostly down and a little bit to the right. So in this region, we're going to have mostly down, a little bit to the right. And by symmetry, if we look directly below, we get mostly up and a little bit to the right. Likewise, over here, we've got mostly down, bent a little bit to the right because of these arrows. So mostly down, a little bit to the right. And up here, mostly up, bent a little bit to the right. So we're getting sort of a general trend. If you've got vectors coming out of or field lines coming out of the positive charge, but bending towards the right because of the negative charge, becoming horizontal and then bending into the negative charge. So we should expect that to look something like this maybe, which matches the idea that we should expect field lines to be emerging out of positive charges and collapsing inwards towards negative charges. Any questions on that general trend so far? So with the general idea that field lines are emerging from this one and entering this one, emerging from the positive source charge and collapsing inwards towards the negative source charge, we can now draw out those field lines. I'm going to erase the individual vectors so we can have some space to work with. But keep in mind that general trend, out of the positive charge into the negative charge. That's generally what we should expect for any electric field lines. And to actually draw out the electric field as field lines, the approach I usually use is start off looking close to one of the charges. If we had just a positive charge, we'd expect just lines going out in all directions. Something like that. And if we're talking about very close to the positive charge, the effect of that positive charge is very strong, and the effect of other charges further away is very weak. So very close to a source charge, you can treat that source charge as the only thing in existence. Likewise, this negative source charge, if that were the only thing in existence, we just expect straight line field lines going straight into it. But since these are not the only, since each one of these is not the only thing in existence on its own, we would actually expect the field lines to bend. For example, this diagonal field line, if it was just the positive charge, we'd expect this diagonal field line to go in a straight line forever. But the fact that there's this negative charge makes field lines go inwards towards it. So this field line is actually going to bend inwards towards this one and join up at this point. Same thing with this one below. This would go just diagonally down and to the right forever if the positive charge were the only thing in existence. But the negative charge biases it and bends it inwards towards that negative source. So something like this. And note that these lines are packed fairly close together, signifying a strong electric field in that region. Meanwhile, this field line, if the positive charge were the only thing in existence, this field line will be going straight down forever. But instead, it gets biased in which direction? instead of going in a straight line, what would this negative charge do to that vector? Would we expect it to be pointing a little more towards the negative charge or a little more away from the negative charge?
Towards, so a little like to the right?
Yeah, because we've got a vector, we're adding the vector that we'd expect from just the positive charge plus the vector, the inwards vector we'd expect from just the negative charge. The one from the negative charge is weaker because it's further away, but that biases it a little bit to the right, so down and to the right. And in fact, this entire field line is going to curve towards the negative charge as a result of that. So instead of just going straight down, this is going to, it starts off going straight down, but it almost immediately starts to bend towards the negative charge. Same thing above. This would be going directly straight up, but instead it gets biased towards the negative charge. So something like this. Similarly, this one would go diagonally down and to the left forever if the positive charge were the only thing in existence, but instead the negative charge biases it to bend around towards the negative end. And because of symmetry, we're going to get exact mirror image left and right. And it's going to bend and loop into this slot here. Same thing with this one. This one goes out, up and around, and loops back in here. And then this one, this is the one exception. Usually we expect every field line to start at a positive source charge and end at a negative source charge if possible. This one though, since it's perfectly horizontal, it can't really bend up or down. Neither one gets influenced in those directions. It just goes straight out. So this one starts at a positive charge, but instead of ending at a negative charge, it goes out to infinity. Likewise, this field line, it does end at a negative charge, but instead of starting at a positive charge, it's coming in from infinity. So every field line starts either at a positive charge or coming in from infinitely far away, and either ends at a negative source charge or keeps going out to infinity. But this would be the characteristic shape of the electric field from a dipole. If we're treating this dipole, this object that's got a positive charge on one end and a negative charge on the other end, if we're treating this dipole as a source charge, the electric field it creates is going to be shaped like this. And of course, it should really be three-dimensional. This is just a two-dimensional cross-section that represents the general idea. But really, you've got electric field from the positive charge coming out in all directions and collapsing into the negative charge in all directions, or from all directions. So it should really be a three-dimensional rotation of this whole thing. But this is generally how we would draw it out. And of course, this should connect up here. I just ran out of room. Any questions on that general shape so far?
So like the dipole will always be from like a positive charge and heading towards a negative charge, is that?
Electric field, not just dipoles, but electric fields in general. In general, if you've got a single location that electric field lines seem to be emerging from in all directions, you know that that location has to have positive charge. And likewise, if you've got a location where electric field is sort of collapsing in towards, you know that location has to contain negative charge.
Okay.
And this is one example of what's usually called Gauss's law. If you've got some region of space like let's say we look at this region of space. Have you seen the idea of electric flux yet? Does that look like a term you've seen in class yet?
I can't speak for the rest, but I don't remember. Maybe I know we talked about Gauss's law a bit though.
Okay. Flux is basically defined as the extent to which field lines are going into a region like this. Like in this case, note that at this location, electric field vector is going into the region, and likewise at this location. So we would treat those as, actually, if it's going into the region, we call that a negative amount of flux. the way we define flux, if the field lines are going into the region, we call that a negative amount of flux. But also over here, we've got regions where the field lines are going out of the region in question. So we describe that as a positive amount of flux. And if we add those all together to get the total flux, to what extent do we have flux here? If we've got these going into the region and these going out of the region. If you add together this negative amount plus this negative amount plus this positive amount plus this positive amount, what would you expect the total to be?
Would it just all cancel out?
Yeah, so we'd end up with the flux in this region is 0. And you could sort of imagine flux as like, if you imagine the electric field as like fluid flowing, the flux is basically saying to what extent is fluid accumulating in this region or leaving this region. If you had more going out than going in, that means overall fluid is leaving the region. So there would be some flux involved. Or if there was more going in than going out, you'd have a negative amount of flux. But it looks like in this region, the flux is 0. Or if we were to draw out, let's say, this region over here, it looks like we've got 3 arrows going in, but also 3 arrows going out. So in this case, the flux is also 0. Is it possible to draw a region where the flux is not 0, where you don't have equal amounts going in versus going out?
Maybe if there's only like 2 going in and like 3 coming out, or like vice versa, or would that not be?
Can you draw a region like that? Like if I draw anything that's crossing a couple of these lines, to complete the loop, or to complete the boundary, I'm going to have to cross those lines again, right?
Right.
Unless I draw a region around what? Is there any way I could draw a boundary so that all the lines are going in or all the lines are going out?
Wait, could you repeat that again? Sorry, Casey.
Is there any way I could draw a region like this, but that doesn't have these canceling out? Is there any way I can draw a region where all the field lines are pointing inwards to that region or all the lines are leaving that region?
I don't know if this is correct, but could you do it like the horizontal lines, like where it says like weak field or
right
like
here?
Yeah, like
here?
Yeah, whichever.
If I draw it here, I've got one line going in and one line going out. So those still cancel each other out and we get 0 flux. Likewise here, still got one going in, one going out. But so far, all these regions we've drawn are just regions around empty space. What if I draw a region that's not empty space inside? Like what if I draw this region? What do you notice about all the field lines crossing this boundary?
They're all leaving, like the flux is leaving.
All of these field lines are going in the outwards direction across this boundary. So that means instead of having some positive and some negative canceling out, all of these would count as positive flux. So you get positive plus positive plus positive, a whole bunch of positives added together. So this has a non-zero amount of flux. In fact, it's got a positive amount of flux, a large positive flux, corresponding to the fact that this region contains positive charge. Likewise, if we draw this region, what are all these field lines doing?
Coming in.
Right, those are all going inwards. So we'll treat that as all negative flux. So we've got negative plus 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 negative. So we end up with a large negative flux, corresponding to the idea that the charge inside is negative. This is really all Gauss's law is saying. For any region of space, the flux across that region is proportional to the charge enclosed. For instance, this region had no charge enclosed, so the flux across the surface is 0. This region had a negative amount of charge enclosed, so it has a negative amount of flux. This region encloses a positive amount of charge, so it has a positive flux, arrows leaving the region. So this works in two directions. First of all, if you know the charge enclosed inside some region, like if you know where the source charges are, and you draw some region that encloses that charge, you know which direction the flux is going overall, based on whether the charge inside is positive or negative. Likewise, if you draw a region that encloses no charge, you know you've got to have the same amount of arrows going in as going out. But this also works in reverse. Also works in reverse. If you don't know where the charges are, let's say all you know about a region is the electric field. You're just taking measurements of the electric field, and you find that the electric field looks kind of like this. If you just take a bunch of electric field measurements and find they look like this, what has to be going on at this location? If all these electric field lines are pointing inwards, or even if most of them are pointing inwards and you've just got a few pointing outwards, what's the only sort of thing that would cause electric field to be going inwards towards that point?
Is it a negative charge?
Yeah, we've got to have a negative charge there. And ultimately, whether we're doing this formally or informally, we're using Gauss's law to know that. The fact that all these electric field lines are pointing inwards, if you imagine drawing a boundary there around this mysterious point in space, all these field lines crossing the boundary in the inwards direction, that's a negative amount of flux. So Gauss's law says if this region is associated with a negative amount of flux, then there has to be a total negative amount of charge inside that region. So even if you don't know where the charges are, if all you have is a map showing the electric field lines in this region of space, you can make educated guesses about where the charges are and what types of charge they are. If you've got a whole bunch of field lines going inwards towards a single point, you can assume there's negative charge there. If you've got a single point that a lot of field lines are coming away from, you can assume that there's positive charge there. So a map of the electric field can guide you towards where the source charges are, even if you didn't already know that, where they are. Any other questions on that so far?
Casey, I have a real quick question. This is back to like something you drew a little bit earlier. The flux at the lower left-hand side of the circle.
This here?
Yeah. So I guess I'm having a little bit trouble seeing why that's a flux of 0 when it looks like all the arrows are like going like towards the negative. Like, if that makes
well, the field lines are just this continuous flow or continuous direction.
Mm-hmm.
In terms of flux, we describe direction based on is it entering the region or leaving the region. So right here we've got arrows entering the region. Here we've got arrows leaving the region. For purposes of calculating flux, those are treated as opposites, entering versus leaving.
That makes a lot more sense. Thank you.
Mm-hmm. Any other questions on this field line diagram or flux or Gauss's law so far?
Casey, could you explain one more time why the weak field line goes to infinity and is kind of like the exception to the
this one?
Yeah.
Yeah, if we take a look at that field line specifically, if we were looking at just the positive charge, we'd expect an arrow to the left that just keeps going out to infinity. The presence of the negative charge, we would usually expect to bend that. But the thing is, if you bend, there's not really any specific reason to bend upwards or bend downwards because we've got complete symmetry here. The negative charge, like if the negative charge were a little bit above the axis, it would bend upwards. If the negative charge were a little below the axis, this field line would bend downwards. But if this is exactly on the axis, parallel to this field line itself, there's not really any specific reason to prefer bending upwards or downwards, so it just keeps going straight. And we can also see this from the vector addition. If we take a look at just the vector, the electric field caused by the positive, that would be to the left and strong. We call that E plus, the electric field caused by the positive charge. What would the electric field here look like caused by the negative charge, negative source charge?
It would look the same going towards the negative charge.
Yeah. Although it's also going to be a good deal weaker. So parallel, but in the opposite direction. And why would that be weaker?
It's further away from the negative charge, so then it's weaker.
Because we expect the electric field magnitude to be K times absolute value of charge divided by R squared. We're assuming it's the same amount of charge, but if we're a lot further away, we're dividing by a much larger denominator. So electric field contribution from the negative source is going to be much weaker simply because it's further away. When you add those, if you got a vector to the right plus a vector to the left, you're not really bending the direction. It's still going to be to the right. It's just weakened because these partially cancel out. So if the vectors you're adding are parallel, there's no change in the direction. You're just going to get one of those two directions and with a modified magnitude because they're partially canceling out. Any other questions on that so far? All right, then let's see if we can get the idea of voltage out of this also. Voltage or electrical potential is a very similar concept to electric field, but also modified in some ways. Let's say you have, let's say we know the electric field. Let's say the electric field in some region of space, let's say we just have a constant electric field of, let's say 10 newtons per coulomb everywhere. A uniform electric field, same everywhere in space. Presumably this is caused by maybe there's a large positive charge over here, a large negative charge over here, and we're in the small space between them. Let's say we put a source charge or a test charge here. Let's say positive 3 coulombs. How much force would that experience from the electric field? What would be the force that that charge experiences?
Is it like 10 times 3?
Yeah. The electric force should just be the test charge times the electric field in that region of space. We're assuming the electric field is 10 newtons per coulomb to the right everywhere. So we just multiply that vector by the charge that we're putting there. 3 coulombs times 10 newtons per coulomb to the right is just 30 newtons. So that would be the force that this experiences. But let's say we wanted to move that. I mean, if you were just applying 30 newtons of force, you could hold it in place. But let's say you want to slowly move it to a new location. And let's say we want to move it a distance of, let's say, 4 meters. Move it 4 meters to its new home. As you do so, you're like, let's say you're just pushing it gradually at a constant slow velocity. You're going to have to apply 30 newtons of force just to counteract the 30 newtons of force that are already on it. So to move it, you apply 30 newtons of force to the left. And if you're applying a force on this moving object, what are you doing? What do we call a force applied across some distance?
Work.
Yeah. You are doing work as you push it. We can even calculate the amount of work. Work is force times distance. You're applying 30 newtons of force just to counteract the electrical force. You're moving at a distance of 4 meters. So you are doing 120, 30 times 40, and then newtons times meters is joules. So you're doing 120 joules of work. You're investing 120 joules of energy into this object. You're not making it go any faster. We're assuming you're just pushing it at a constant speed, which is why you have to apply exactly as much force as is needed to cancel this out. We don't want it to accelerate. We just want it to move at a steady pace. No change in speed means no change in kinetic energy. So what type of energy are you giving to it? If you're pushing something against an existing force, what would you call the kind of energy you're providing? Yeah, we would say it's gaining potential energy. By doing 120 joules of work, but not changing the speed, you're investing 120 joules of potential energy into it. So as this travels, it's gaining 120 joules of potential energy. This path represents a change in potential energy of plus 120 joules. We're giving this 120 joules of extra potential energy above and beyond whatever it already had. And then we would call this electrical potential energy because it's associated with the electrical force. Any questions on that so far? What if we used a different amount of charge? Let's say we go through this same process, but with, let's say 5 times as much charge. Let's say we had a 15 coulomb object. How much force would that be experiencing?
150.
Yeah. Charge times electric field is 150 newtons, which means to make sure this is moving steadily instead of speeding up or slowing down or falling the other direction, you need to apply your own force of 150 newtons. And let's say we want to move this along the same path. We're starting at the same location as the 3 coulomb charge did. We want to end at the same location the 3 coulomb charge did. So let's say we're moving this one a distance of 4 meters also, to put it at the same ending location as the other one. So if we calculated the same work, force times distance, which tells you the change in potential energy involved here, what would be force times distance in this context?
600?
Yeah.
I think.
150 newtons of force times 4 meters of distance is 600 joules. So by doing work to move it against the force, we are investing an extra 600 joules of potential energy into it. So these two objects are both moving along the same path, but they involve different changes in potential energy because they have different charges. And it's proportional as well. This one is 5 times as much charge. It also costs 5 times as much work, 5 times as much increase in energy to make it happen. So these are proportional. The change in potential energy, even though they're traveling along the same path, the change in potential energy is proportional to the charge in the same way that the force is proportional to the charge. That suggests that change in potential energy should equal charge times something. Anyone know what we call that something? If we examine the units, energy as always is measured in joules. Charge is measured in coulombs. So what would this mysterious new quantity have to be measured in order for this to work out?
Is it joules over coulomb?
Yeah, because we need to cancel out coulombs and introduce joules. And we briefly talked about joules per coulomb in 7b when we were looking at electrical circuits. Joules per coulomb is volts. And as a result, we call this quantity voltage. More formally, it's referred to as the electrical potential, not potential energy, but electrical potential, a different quantity. But informally, it's usually just called volts or voltage. So this is the voltage, or more formally, electrical potential. So electrical potential is just another word for voltage. Electrical potential energy is not the same thing, but they're related by charge itself, the test charge as a multiplier. So if we look at that ratio, because we can solve for voltage, delta V, by just dividing both sides by charge. So if we try that here, the change in potential energy divided by the voltage, change in potential energy divided by voltage. What's 120 divided by 3?
40.
So we would say the change in potential, the change in voltage is 40 joules per coulomb or 40 volts. Same thing here, 600 joules divided by 15 is also 40 joules per coulomb or 40 volts. So even though these different charges are experiencing different changes of potential energy, the ratio is the same. The ratio of potential energy per coulomb is the same. So let's say this particle gains 120 joules as it moves along this path. This particle gains 600 joules of potential energy as it moves along the path. But the path itself, regardless of what particle you put there, the path is a 40-volt path. In fact, we could even treat this as a field. The voltage is just a value at each location in space. This region is let's say a 0-volt region. If we just define this location to be 0 volts, move over here, this entire region is a 40-volt region. So very much in the same way that when we were looking at electrical circuits in 7B, we were able to assign a voltage at every location along the wire. Here we're doing the same idea, but instead of just confining it to a wire, we're looking at this open space. We're saying this region of space is a low voltage region of space. This over here is a high voltage region of space. And if you know the difference in voltage of some path from initial to final, you can multiply that difference by the charge of the object you want to move along that path to figure out the amount of work that would be required, the change in potential energy associated with moving that particle along that path. So potential energy is associated with the particle, including its charge. Voltage is associated with the location in space, whether there's a particle there or not. So in this way, it's very similar to the relationship between force and electric field. Force is a property felt by the particle at that location. Electric field is a property of the location, whether there's a particle there or not. Same idea here. Potential energy is a property felt by that particle as a result of its location. Voltage is a property of the location in space, whether there's a particle there or not. And in both cases, you use charge to convert back and forth. Electric field times charge equals force. Electrical potential times charge equals potential energy. Any other questions on that so far? And if you go to, let me put a link to the chat here, mathandcheese.org/P7C/electricalquantities.pdf, there's a chart showing how all these quantities are related to each other: voltage, potential energy, electric field, and force, and how to convert back and forth. So take a look at that if you need a reference sheet. Feel free to email me if you have any other questions, and I will see you next time.
Thank you.
You're welcome.